Hello everyone. In this lecture, we will study about posets. In our previous lecture, we already studied some definitions required to study about posets. So let's now start. Definition of poset. A relation less than equal to on a set A is called a partial ordered set relation or an order if less than equal to is reflexive, less than equal to is antisymmetric, and less than equal to is transitive. Here less than equal to is a notation for a relation. So if these three conditions are satisfied by a relation, then we say that relation is a poset, which is partial ordered set. We already studied about reflexivity and transitivity in our previous lecture, so we will now know about antisymmetry. Antisymmetry, a relation less than equal to on a set A is called antisymmetric if this happens. A less than equal to B and B less than equal to A, then A is equal to B. मतलब अगर A B से related है और B A से related है तो A को B के equal होना होगा तभी हम उसे antisymmetry कहेंगे. Let's take an example. A is equal to 0, 1, 2 and the relation is 1 is related to 0, 0 is related to 1 and 2 is related to 2. Here R is not antisymmetric as 1 is related to 0 and 0 is related to 1, but 0 is not equal to 1. Hence, it is not a poset because it is not satisfying this condition. Let's go to next slide. Some examples of posets. We take the set of real numbers and regular less than equal to with regular less than equal to relation, then it is a poset. We can prove this by reflexivity. We see for all x belonging to R, x is related to x because let's take a number 2. So 2 is equal to 2. So it is satisfying this 2 is less than equal to 2. So reflexivity is satisfied. Now come to transitivity for all x, y, z belonging to R. If x is related to y and y is related to z, then we have x is related to z. We can verify this by taking let's say x is equal to 1 and 1 is less than equal to 2 and 2 is less than equal to 3. So we know that 1 is less than equal to 3, which is this, and it is valid for all real numbers. So this is satisfied. Now antisymmetry for all xy belonging to R. If x is less than equal to y and y is less than equal to x, then x is equal to y. If we take x is equal to 1 and y is equal to 2, then we cannot say 2 is less than equal to 1. So this condition is not valid here. This can only happen when 1 is equal to 1. So it is already verified. Next example, let x be a set, then we take power set of x with containment relation, then it becomes a poset. We now show the three properties. Reflexivity for all A belonging to power set of x means for all subsets of x, we know that A is a subset of itself. So it is reflexive. And now we come to transitivity. Let A, B, C belong to power set of x. If A is a subset of B and B is a subset of C, then for all x belonging to A, we have x belonging to B because A is a subset of B. Then, therefore, x belongs to C because B is a subset of C. And hence, A is a subset of C, and which proves this relation is transitive. Now anti-symmetry for A and B belonging to power set of X. If A is a subset of B and B is a subset of A, then A is equal to B by double containment. Let's move to next slide. Here are some more examples of posets. If we take the set of natural numbers with relation divisibility, it forms a poset because x divides x for all x belonging to natural number set. Take any number 3, let's say 3. So 3 divides itself. So it is reflexive. And now we take anti-symmetry. If x divides y and y divides x, we have x is equal to y. Let's say 2 divides 4. So this condition is only valid when x is equal to y, because we cannot say that 2 divides 4 and 4 divides 2. We only say 2 divides 2, so x is equal to y. Next, if x divides y and y divides z, then we have x divides z for all natural numbers. So this shows that it is transitive too, so it becomes a poset. Next, we have a definition. Let A and B the elements of a poset, A less than equal to. Then the elements A and B are said to be comparable if either A is related to B or B is related to A. मतलब या तो A को B से related होना पड़ेगा या फिर B को A से related होना होगा. अगर ऐसा नहीं है तो हम कहेंगे कि ये incomparable है. Next definition. A hash diagram is a graphical representation of the relation of elements of a partial ordered set. A point is drawn for each element of the partial ordered set and joined with line segments according to the following rules. So it is just a graphical representation of relation of elements of poset. And हर एक पॉइंट के लिए, हर एक एलिमेंट के लिए हम उसे एक पॉइंट से डिनोट करेंगे और एक लाइन सेगमेंट से ज्वाइन करेंगे दो पॉइंट्स को इन रूल्स के अकॉर्डिंग. So these are the rules. If P is less than equal to Q in a poset, then we make a point corresponding to P and we make a point corresponding to Q, and P is appearing lower in the drawing than the point corresponding to Q. Means like, let me show with a diagram. Let this is P and this is Q. So P is less than equal to Q, then P is drawn lower than Q, and we connect these. So next is the 2 points P and Q will only be joined by a line segment if and only if P is related to Q. Means अगर P Q से related है तो इन दोनों पॉइंट्स के बीच में एक लाइन सेगमेंट होगी ही होगी, और अगर दो पॉइंट्स P एंड Q लाइन सेगमेंट से ज्वाइंट है तो इसका मतलब ये है कि P Q से रिलेटेड है. And the last one is, there is no horizontal line segment allowed in a hash diagram of posets. We only have vertical lines. Let's go to another slide. So these are some hash diagram examples. Let's take this set. This is the set for divisors of positive divisors of 12. 1, 2, 3, 4, 6, and 12, and the relation here is divisibility. You can easily check that this is a poset by verifying all the three conditions, which is anti-symmetry, transitivity, and reflexivity. And now we make the hash diagram of this. Here we see that because the relation is divisibility, so in this diagram we see that 1 is joined by a line segment with 2. So 1 is related to 2, means 1 divides 2. And here 1 divides 3, 1 divides 4, 1 divides every element. So 1 is connected to every element. You can check this. And here 3 is dividing 9, so it is joined with this. 3 is dividing 6, 2 is dividing 6, 6 is dividing 18, 18 dividing 36, 6 dividing 12, and 12 and 18 are both dividing 36. Here also 6 and 9 are both dividing 18. And in the similar way, 8 is dividing 24, 24 is dividing 72. And in this way we can draw this diagram. So another example, we already saw that a power set of a, a power set with containment relation is a poset. So we now draw its hash diagram. This is phi, which is empty set. So phi is related to the singleton set A, B, and C. And C is, because C is contained in this set A, C, the set containing A and C. So A is contained in this set, C is contained in the set AC, and C is also contained in the set BC. B is contained in the set BC, and A and B are both contained in the set AB. And these three sets with two elements AC, AB, and BC are all contained in the set ABC. So this is the hash diagram of this poset. Next is natural numbers with usual less than equal to relation. You can check that it is a poset. So hash diagram will be a chain, which means it is only a vertical line. We connect all the elements. 1 is related to 2 because 1 is less than equal to 2, 2 is less than equal to 3, and hence it forms a chain, and it is an infinite chain. So it has no greatest element, it has just a least element 1. Now we look at this discrete order of 4 elements. Discrete order means no element is related to any other element. So there will be no line segment because none of them is related to any. So A, B, C, and D with no line segments. So thank you. That's all for today. I hope you liked the video.